Yep, we're live.
Great, thank you.
Yeah?
Yes.
Oh,
Thanks.
okay.
Bye.
Love you. Bye.
Okay, hello everybody. And get started. I know some people are still joining, but it's after 12:25, so let's get started. So today we're going to be talking about statistical inference and hypothesis testing. This is going to be going back and building on some of the statistical stuff that we talked about in lecture 4. So we'll talk about statistical inference, central limit theorem, hypothesis testing and the z-test, confidence intervals a little bit, A/B testing as an interesting application. I will say this lecture's, I think, on the long side, but the one for Thursday is short. So my plan is to at least get through parts 0 and 1 today, and then maybe we'll do part 2 on Thursday. We'll see how the time goes. Okay, so there's a Wired article as part of the reading for
Let's
today.
zoom in a little bit on your browser.
Oh, yeah. Is that better?
Yes, thank you.
So there's a Wired article as part of the reading for today, and also some Planet Money episodes, which are, some interesting discussions of statistical inference. So check those out. Okay, so this is going to be kind of a lot to cover in a lecture. So for a more complete treatment, you probably want to take a whole course in statistics, but we are going to do just a little overview here. So to get started, we'll do all of our imports. Okay, and then we're importing pandas, numpy, and lots of different functions from scipy.stats, different distributions, and the plotting functionality that we have used before. Okay, so let's kind of recap what we discussed in lecture 4. In lecture 4, we were doing descriptive statistics. This lecture, we're doing inferential statistics. The basic difference is if somebody gives you a data set, you can compute statistics on it. You can compute the mean, the standard deviation, the median, etc. However, what you're more interested in general is to analyze that data set. And from that data set, which is a sample from some population that you want to learn about, you want to infer something about the population. So not just that data set, but what can you say about the population it was sampled from? That's the idea of statistical inference. And we discussed 2 main types of random variables. So first of all, discrete random variables and random variables. Discrete random variables take on a discrete set of values, and their probabilities, the associated probabilities with those discrete values, are described by a probability mass function, or PMF. So we would write the probability that the random variable x is equal to value k as some function f of k. Okay, and some of the most famous discrete distributions include the Bernoulli distribution. Variable can be 0 or 1. So the PMF just takes on 2 different values, p and 1 minus p. And you can think of p as like the success probability when you have a random event, like a coin toss or something like this. And so for a Bernoulli, the mean is p, and the variance is p times 1 minus p. Okay, so the Bernoulli distribution with a p of 0.5 would describe a fair coin toss, right? You have a 50% getting heads, 50% chance of getting tails. If the coin is unfair, then we would have p not equal to 0.5. It's, more likely to get either heads or tails. Okay, and so another famous discrete distribution is the binomial distribution. And you can think of the binomial distribution as being constructed from the Bernoulli distribution as follows. So if you have n independent Bernoulli trials and you count the total number of successes in that sequence of trials where each individual trial has success probability p, then, and you add up how many successes altogether you get, that random variable has a distribution, and it has a PMF function described by this right here. Possible values between 0 and n, so k ranges from 0 to n. However, we don't actually have to, code this formula, although you can, but remember that Python has all of these functions built in. All of the for the commonly used distributions. So for example, if we wanted to get a plot, let's say we're looking at a binomial random variable with an n of 10 and a p of 0.5, then we can define a function f, simply the binomial PMF. So this maps k to the PMF evaluated at k. And then we can plot this, right? We get our range of values from 0 to n, and then plot the PMF of the binomial random variable. And you notice it looks a little bit like a bell, but a little bit of a spiky bell. There aren't that many different values here. Okay, so a couple of facts about the binomial distribution. Yeah, I think I already said that. So yeah, we think of it as the total number of successes in n Bernoulli trials. The mean is n times p, and the variance is np times 1 minus p. One of the other distributions that you encountered in the homework is a Poisson distribution, which is also discrete. Okay, so now let's recap continuous random variables a little bit. So unlike discrete random variables, for a continuous random variable, the probability of taking on any single specific value is always 0. So it doesn't make sense to talk about the probability that a continuous random variable equals 2 or 5 like this. So for continuous random variable, it only makes sense to talk about the probability of it being in a range of values. And you compute the probability of it being in some range of values between A and B by integrating from A to B the corresponding probability density function, or PDF. So the PDF of a continuous distribution completely describes that distribution. It'll determine the mean, the variance, and anything you want to calculate in terms of probabilities. Okay, and I see a habit that I'm just now seeing. Will there be any exercise lecture? No, thank you. Thank you. We're going to skip the exercises today because we have a lot to cover. Okay, and if you remember from your calculus class, if this is a non-negative function, the integral from a to b of little f can be interpreted as the area under the curve, the area under f between a and b. Okay, so the most famous continuous distribution is the normal distribution, and it has the following PDF function. You can notice two parameters in this formula, a mu and a sigma, and so this is a two-parameter family of distributions, sometimes referred to as the bell curve. Okay, so let's take a look at the plot. So a standard normal distribution has mean 0 and standard deviation 1. So we can plot that. First, I can define my mean and standard deviation, and then a range of values that basically goes from 4 standard deviations below the 4 standard deviations above the mean, and then evaluate the normal PDF on that vector x with that mean and standard deviation. Okay, and so you can see here in this plot, this is the plot of the PDF of the standard normal variable, and it is a nice bell curve that decays pretty rapidly as you get far out from 0. Okay, and so some facts about this distribution: the mean is mu, the variance is sigma squared, and like I said, for any continuous random variable, the probability of being between A and B is obtained by integrating the PDF. However, it's often really handy to use the cumulative distribution function to evaluate integrals of this type. And the cumulative distribution function, usually denote with a capital F of x, is the probability that the random variable x is less than or equal to little x. And so that is just the integral from -infinity to x of the PDF. And so you see that you can always break up an integral from a to b as the integral from -infinity to b minus the integral from -infinity to a. And then you can see that each of these is equal to a CDF at a certain point. So we can evaluate an integral of this type as capital F of b minus capital F of a. So this is really convenient. So we don't have to actually deal with integrating things. We can just call the CDF function. And again, these are all built into Python for all of the common distributions. Okay, so in here, you can see a plot of the CDF of the standard normal distribution. So this is the exact same kind of plot, except here we're plotting the CDF. So you can see as x goes to negative infinity, for really small values, the CDF is close to 0. And it always grows. It's always an increasing function. And for really big values, it's close to 1. Okay, so let's just do a few examples here so we can kind of practice interpreting probabilities and PDFs and CDFs. So what does this integral mean? The integral from minus infinity to 1 of little f. So this is the probability that a normal random variable is less than 1. And I should say it doesn't matter if you say less than 1 or less than or equal to 1. Whether you include the boundary doesn't really matter. And this is also the CDF evaluated at 1. So I can evaluate this with the norm.cdf function. And I can see that for this standard normal random variable, there's a probability of 0.84 of being less than 1. Okay, so next I'm calculating what's the probability that my norm is between minus 1 and 1. So this is the CDF evaluated at 1 minus the CDF evaluated at negative 1. And again, using the norm.cdf, I see that this is 0.68. The 68% chance of being between minus 1 and 1. And actually, this 68% chance is universal for any mean and standard deviation. The probability in a normal distribution of being within 1 standard deviation of the mean is always 0.68. Okay, and then this one, I guess, is easy, right? If you integrate from minus infinity to infinity, you're just saying, well, what probability that the normal takes on any value, which has to be 1, and you can also call the CDF function with an argument of infinity. This is from the SciPy package, and minus infinity to evaluate that explicitly. Okay, and then here, if we integrate anything from 1 to 1, we just get 0. This sort of reflects the fact that for a continuous random variable, the probability of any one specific value is 0. Okay, so yes, lots of other continuous distributions, but in this class, we'll mostly focus on the normal distribution. Okay, so that was a little kind of recap of what we did before and a little bit more practice or examples with how we get probabilities from the PDF and the CDF function. In the next part of the class, I'm going to talk about statistical inference. Part 2 will be on 2-sample statistical inference. And I will say, usually in most data analysis scenarios, you're interested in 2-sample statistical inference because you're interested in making comparisons between different groups, between different options. This is the idea of the A/B testing. But in order to understand how hypothesis tests work and a lot of the basics, it's really helpful to start with the 1-sample procedures. And a lot of statistical, procedures are only valid under the assumption that a random variable has a normal distribution. So the normal distribution comes up a lot, both in terms of the procedures themselves and in terms of checking assumptions for running those procedures. So we're going to go over a quick check to determine if a normal random variable, to determine if a random quantity has an approximately normal distribution. So let's say we have a sample data set, x1 through x3. So how do you know if it has a normal distribution? Well, one tool that you can use is called the normal probability plot. So in a normal probability plot, what you do is you take your data values, you sort with each data value, you associate a percentile. So, okay, this point is my 5% point, this point is my 70% point, etc. And then once you have those percentiles, you compute what are the values in a standard normal distribution that correspond to those percentiles. And then you can plot your actual data versus those predicted percentiles for a standard normal distribution. The main thing to remember is that it's normal, this plot should look linear. Okay, so here we're going to look at some examples where, remember this function, this .rvs function, is generate random variates from this distribution function. So for this first plot, I'm looking again a standard normal distribution and generating 200 random samples from that distribution. And let's take a look at the plot. This is the normal probability plot. And you can see it is very linear. Now it's not perfectly linear, but this was an exact normal distribution. So even a normal distribution, some deviation from linearity, but you see that overall it's pretty close to linear. Okay, so for comparison, the second plot is from a t-distribution. So we take 200 samples from a t-distribution and look at the normal probability plot. What you notice happening here is it kind of curves up here and it kind of curves down there. Any guesses as to why that's the case or what that's indicating about the t-distribution? Anyone want to put a guess in the chat? We do have a question. Yes, the t-distribution has heavier tails. That is in the case. So the t-distribution has heavy tails, which means it has more extreme values. So, so for a normal distribution, it should kind of stick to this line, but for the t-distribution, these extreme values cause it to go over the line in the large values and under the line in the small values. Let me check my question here. How do you know if a deviation is too much deviation? Is the value associated with it? Right, okay, yeah, good question. So what is too much? I would say too much is usually 2 or 3. There's not like a one right answer to that question. So you can have different cutoffs in probability, different cutoffs for how many standard deviations away from the mean you think is acceptable. And so you'll work with heuristics like that. But I would say kind of ballpark, 2 standard deviations, 3 standard deviations. More than that is very unusual. Okay. So yeah, so because for a normal distribution, 95% of the data is within 2 standard deviations, and I think it's 99.7% is within 3 standard deviations. Okay, so yeah, then
Dr. Little, are you suggesting that there is a standard deviation of your data set compared to a normal?
Well, yes. I mean, I'm sort of saying how many standard deviations away from the mean is usually considered a lot. But those specific numbers, the 95%.
What's the mean you're talking about?
Whatever the mean of the distribution might be. You know, of course, that in general may be unknown. But we will deal today with the problem of trying to make some inference regarding what it is. And so a lot of times that's done by assuming, well, if the mean were this is what we would expect to see. But I think we're getting maybe a little bit ahead of where we're going with it. Okay. So then these last 2, we have a Laplace distribution, and then the last one is a gamma distribution. And so here you'll notice this is the Laplace distribution. That's kind of like a symmetric version, exponential distribution. It is also heavy-tailed, so the decay of the PDF is slower than for a normal distribution. And once again, you see this reflected in the normal probability plot. On the other hand, this is the normal probability plot for a gamma distribution. And what you see here is you see it sort of curving upwards. Anybody know why that happens for the gamma distribution, or what property of the gamma distribution causes that curving upwards in the probability plot? Ah, yes, positive skew question mark. Yeah, indeed, it has to do with skew in the data. In this case, the data is skewed right. So the tail is on the right side of the plot, which means basically all of the extreme values occur for big values, and you don't see extreme values for small values. So that's why you see this kind of curve up pattern. If it were skewed left, you would see the extreme left tail, and you would see it curving downward. And I also have a question: would it be appropriate to do a correlation test to see if the data is normally distributed? Yeah, you could do that, right? So if you want, to get just some of is this a line, you compute the correlation of that plot, it will be some kind of indicator about how linear it is. But I suspect you might get, even for a plot like this, the R value would probably be not tiny. There are hypothesis tests that you can run to actually test for a normality. We're not going to go into those. We're just kind of eyeball it. Okay, so let's get in now that we sort of have, we're equipped with our normal probability plot tool, which will be useful. Let's get into the details of hypothesis testing. And let's start off with an example related to the coin tosses that we have been discussing. So suppose we have a coin and we want to determine whether or not the coin is fair. So how would we do that? Well, we could flip it many times and count how many heads we get. And if the fraction of heads is about 0.5, then it seems reasonable that the coin is fair. However, here it gets a little bit hard to quantify exactly. Well, how close to 0.5 should it be to be considered, normal if the coin is fair? Or how far away from 0.5 should it be, in order to have strong evidence the coin is unfair? Okay, so this is an example of statistical inference. So we're trying to infer about the coin from a sample of coin flips. And if you want to, relate this to a population, think of the population as what would happen if you just kept flipping the coin an infinite number of times over and over and over again. But, we're not doing infinite coin flips. We're only doing it for a fixed n. Okay, so let's say we have n of 1,000. If the coin is fair, then we know the outcome is distributed according to a binomial distribution with a p of 0.5. So let's plot the PMF. We can define this function f, which just maps k to the binomial PMF evaluated at k, and then we can plot this PMF. You see this plot here. And then we're also adding a plot, just a single data point here at 545, because let's assume that when we do our experiment, we end up with 545 heads. So that corresponds to, this blue dot right here. Okay, so we can think how likely 145 heads for a binomial distribution with n of 1,000 and p of 0.5. We know how to evaluate that with the binom.pmf function, and we see it is very unlikely there's only a 0.0004% chance of observing that outcome. This, however, in and of itself is not enough to say that it is an unusual outcome. To really say it's an unusual outcome, what we want to think about is not just the probability of the event itself, but the probability of that event or anything more extreme occurring when we do the experiment or the simulation. Right, so this is the important question. What is the probability of us seeing a value as extreme or more extreme than the value that we observed? Okay, so we don't just want to compute the probability of getting 545 heads. We want to compute the probability of getting 45 heads or more extreme. So we can do that by summing up all of those PMF values of the binomial, starting with 545 and going all the way out to 1,000. Remember, this NP data range does not include the last argument, going 545 to 1,000. And if we print that sum, we'll see it's 0.002. Okay, which is indeed, that's a lot larger than 0.004, but still quite small. So we see that there is only a 0.002% chance, if the coin were fair, that we would get that many heads, a count that large. But one thing to keep in mind when you're doing hypothesis tests is you can get extremes in both directions. So, you can get a count that's much higher than expected, and you can also get a count or a mean that's much lower than expected. And in general, when you're computing how extreme the outcome is, you want to add the probability of both sides. So we also want to compute the probability that when we do the experiment, we get less than or equal to 455. Why 455? Well, that's the same distance away from the mean. The mean is at 500. So we had 545, which is 500 plus 45. We also want to do 500 minus 45 to get 455. So, and then we compute the probability of anything smaller than 455. So that's what this S1 does. So now we have to sum up the binomial probabilities from 0 to 455. Again, doesn't include the last element. And then we sum up the binomial probabilities as we did before from 545 to 1,000, and we just add them together. Add them together, we get 0.0048, which is still a very small number. Okay, so what this is telling us is that if the coin were fair, there's only a 0.49% chance of observing an outcome this extreme. So, right, so if the coin were fair, it's really unlikely that we would see this result. And this is the whole idea behind hypothesis test. So when you're doing hypothesis testing, you have to be a little bit careful about so what we don't want to say is we don't want to say it is unlikely that the coin is fair, or we don't want to say, there's a 0.995% chance the coin is unfair. That's not what we've computed here. Rather, we want to say if the coin were fair, under that assumption, there's only, a 0.49% chance of observing an outcome this extreme. Okay, so when we're doing a hypothesis test, we always specify two different competing hypotheses. So the first is the null hypothesis, written H0. And in this case, the null hypothesis would be that the coin is fair, i.e. P is equal to 0.5. Then we specify a competing hypothesis called the alternate hypothesis, HA, and I think throughout the lecture there's some little a's and some big A's, but they're all the HAs are the alternate hypotheses. And so this is the hypothesis the researcher usually is hoping to validate, is hoping to find evidence for. So in this case, HA is the coin is unfair, I is not equal to 0.5. So one thing to keep in mind for hypothesis tests, the null hypothesis always contains equality, kind of equality, could be a less than or equal to or a greater than or equal to, but always some form of equality, and the alternate hypothesis does not. Okay, and to run a hypothesis test, we have to specify a significance level, alpha, and usually this is taken to be 1% or 5%, and for this there's not a clear, right or wrong significance level to take. Sort of depends on what you think is appropriate for your data analysis. But let's say we choose a significance level of 1%, alpha of 1%. Okay, so first we define the hypotheses we want to investigate, then we collect a random sample. Okay, and so this could be we flip the coin 1,000 times, or this could be we go collect data from a population, but we generate a random sample. In our case, we flip the coin, we get 545 heads. And then finally, assuming the null hypothesis is true, we compute how likely it is to see a number that is at least as far from the expected value as the number obtained from the random sample. Okay, that was this 0.49%. This is called the p-value. Okay, and the p-value is what you want to compare with significance level. If the p-value is smaller, less than or equal to the significance level, then you conclude that you have evidence for the alternate hypothesis. If it's greater than the p-value, you conclude that you have evidence for the alternate hypothesis. Or another way to say that is if the p-value is smaller than alpha, you reject the null hypothesis. If the p-value is greater than alpha, you fail to reject the null hypothesis. Okay, so a couple of comments about the p-value, right? It's always computed under the assumption that the null hypothesis is true. And the smaller the p-value, the stronger the evidence against the null hypothesis, or the stronger the evidence for the alternate hypothesis. And just remember, be a little bit careful when you're writing interpretations with p-values, that the p-value is not the probability that the null hypothesis is true or false. So yeah, I think we've discussed all that. All right, so this is kind of the results of how you run a hypothesis test. But what we did in this example was utilize the binomial distribution. Basically, for our null hypothesis, we were able to say, okay, if this is true, we have a binomial distribution, and we know exactly what the PMF for that is. In general, we want a procedure that's less distribution specific. We want to be able to do a hypothesis test for data with all kinds of distributions. And we want a more general procedure, and we can get one utilizing the central limit theorem, which will be our next topic of conversation. So we've got a question here. So in this instance, we could say that the coin is fair with up to 9.5% confidence. Okay, no, we could not say that actually. We can, because the coin here to be unfair. So in this example, the alternate hypothesis was that the coin was unfair. But if you change fair to unfair, then, well, sort of, what we would say is that there is strong evidence that the coin is unfair. Because if the null hypothesis were true, then there's only a 0.49% chance of observing an outcome as extreme as what we observed, and that's pretty small. Okay, hopefully that answers your question. It takes, if you haven't seen hypothesis tests in any courses before, it does take a little bit of practice, kind of getting your head around exactly how we state the hypotheses and exactly how we state the conclusions. Okay. All right, so the central limit theorem. All right, so one of the reasons that the normal distribution is so important in statistics is the following theorem, known as the central limit theorem. And what does it say? So let's say we have a sample, x1 through xn, of n random variables, which are, we would say IID, so they're independent and identically distributed from a distribution with mean mu and finite variance sigma squared. Then, if n is large, conclude that the sum of the variables is approximately normal with a mean of n times mu and a variance of n times sigma squared. And if we look at the sample mean, so we take the sum and we divide by n, the total number of random variables, the mean is also approximately normal with a mean of mu and a variance of sigma squared over n. Okay, so let me emphasize what was not stated in the theorem. There was no kind of distribution assumption on the x's, right? The x's could be from a Bernoulli distribution, or they could be from a Poisson distribution, or they could be from, a distribution that's really skewed. But even so, if we have a lot of observations, the sum and the mean will have an approximately normal distribution. So that's kind of interesting, right? You can start off sampling from skewed distribution, but as you collect more and more data and you look at the mean, it will converge to a symmetric distribution. It will converge to a normal distribution. Okay, so how can we use this? Well, let's see how we can use this in the example that we were talking about with the coin flips. So we know that the binomial random variable is the sum of n Bernoulli random variables. Let's see what the CLT then tells us about that distribution. So it says that if n is large, a binomial random variable will be approximately normal. So if we flip a coin many times, the number of heads that we're likely to see can be described by a normal distribution. And that means we could have computed the p-value or approximated the p-value using the normal distribution instead of the binomial. So let's sort of use this procedure to answer how unlikely is it to flip a fair coin 1,000 times and see 545 heads. Okay, so supposing we flip the fair coin 1,000 times, how many heads do we expect to see? And let's use the CLT approximation. So the CLT says that the number of heads we see is approximately normal with mean n times mu. Now the mean for each individual x is p. And so because it's a Bernoulli, so we get 1,000 times 0.5, which is 500. And the variance is n times sigma squared, or n times p times 1 minus p, because that's the variance for the Bernoulli, and that is 250. So we know that this binomial distribution is approximately normal with a mean of 500 and a standard deviation of 250. See how good that approximation is. So we can do that with a simulation. Okay, so we can, first of all, sample 10,000 random variates from the binomial distribution, and we can make a histogram of those values, and then we can overlay that histogram with a plot of a normal PDF with mean, what we computed here, so a mean of n times p, or 500, and a standard deviation of 250. And so let's see what that looks like if we sort of make these plots. So here you can see the histogram of the binomial, and then you see the density curve of the corresponding normal approximation. It's very close, right? So this is a really good approximation for this distribution. Okay, and if we want to do our little normality test with the normal probability plot, we can also do that. So we're going to do this prob plot. This is from the scipy.stats package. We imported that at the beginning of the lecture. And when we call that, we see this is very linear. Okay, so we get a very, very good match between this distribution, this binomial distribution, the large N, and the normal distribution. Okay, so now if we want to actually compute the p-value, that's always a hypothesis test, to figure out, okay, what's the probability of getting something as extreme? We want to compute the area in the tails. Sometimes it's easier, however, to compute the area in the bulk and then just do 1 minus that. So if we do that, we can just integrate from 455 to 545 of our PDF, or the difference of the CDF. And let's see what. Okay, so here with an N of 1,000 and a P of 0.5, we compute the mu and the sigma as predicted by the CLT. And then we do the CDF at 545 minus the CDF at 455. That comes out to 0.9955. Again, that's the area in the bulk. We do 1 minus that to get the area in the tails, which is 0.0044. So that's pretty close. What we had before, 0.0049. Now this is 0.0044. So we see that this approximation was very accurate. Okay, and then if you want to kind of visualize, the area in the bulk versus the area in the tail, you can use this this fill between plot to kind of fill in some range of values. Okay. Okay, so again, we see that 99.5% of the time we would see an event less extreme than 545 heads. Okay, let me take a break there. I probably should have braked like 5 minutes ago, but that's a good stopping point. Let's take our 5-minute break, and then we'll come back at 1:15 for the rest of the lecture. Okay, see you back at 1:15. All right, let's go ahead and get started back from our break. So let's just look at a couple more examples of hypothesis tests. So here's the freshman 15. So you know it's sort of a common belief that that first year college students tend to gain weight, and how much weight? About 15 pounds, right? This is called the freshman 15. So let's actually do a hypothesis test to see if this is actually valid. So let's let mu denote average weight gain in the first year of college. And we'll take the null hypothesis to be that mu is greater than or equal to 15. So the alternate hypothesis, average weight gain in the first year of college, is less than 15. The alternate hypothesis here, mu less than 15. So they've set up this test, and you kind of want to be mindful when you're setting up your hypotheses, set it up the way you want, because a hypothesis test will allow you to conclude evidence for the alternate, but it never allows you to conclude evidence for the null hypothesis. So if we want to sort of debunk the freshman 15 legend, then we want our alternate hypothesis to be mu less than 15. See if we have evidence for that. Okay, let's once again pick a significance level of alpha of 1%. Now, let's suppose that we have a random sample of N students and their weights before and after the first year of college are measured. And from this random sample, you compute a sample mean, X bar, and sample standard deviation, S. Okay, so an article in the journal Obesity cites such sample for 137 students, and the data yielded a sample mean weight gain of 2.42 pounds with a sample standard deviation of 5.72 pounds. Okay, so we might think, okay, 2.5 pounds, that seems a lot less than 15. So it seems, you know, just from looking at the data, the alternate hypothesis seems reasonable, but we want to actually quantify a p-value associated with it so that we can argue more precisely regarding the evidence. All right, so assuming the null hypothesis to be true, how unlikely is it that we would observe such a small value, right? 2.42 pounds. So let's remember what the CLT tells us. So the CLT tells us that the mean, the sample mean of these variables, X bar, and let me make a little comment here that throughout the lecture, when I use a capital X, this is denoting a random variable. And when I use a little x, it's denoting a specific outcome of that random variable. So here, the big X is the random variable sample mean. And here, sorry, the big X bar, here the little x bar is what the specific sample mean came out to be in our data set. Okay, so the CLT says that the sample mean has an approximately normal distribution with a mean of mu and a variance of sigma squared over n. Okay, so, well, what's mu? The mu that you want to use is always the mu value that appears in your hypotheses. So if we go back and look at our hypotheses, we see that the null hypothesis is that mu is greater than or equal to 15. So we want to take mu to be 15. And so that's where we get mu of 15. And variance, okay, the CLT says that you get a variance of sigma squared over n, where sigma squared is the standard deviation of each of the random variables. There's a little bit of a, what should I say? A little bit of an approximation here. You don't actually know the true standard deviation sigma. You have to approximate it with the sample standard deviation. So that's why you see, S here instead of sigma. We would like sigma, but generally we don't know it, so we usually have to use the S instead of sigma. But that's okay. Let's just use the sample standard deviation of 5.72, plug that in, and we see that we would expect a standard deviation of about 0.2388. Okay, so then we can compute, all right, well, what's the probability that the sample mean is smaller than 2.42, right? If the null hypothesis is true, if the mean weight gain really is, at least 15 pounds, the probability that we would observe in our random sample a sample average that is, 2.42 or smaller. So the probability that this X bar is smaller than 2.42, I could have also put less than or equal to. Either way, the probability, the p-value comes out the same. From minus infinity to 242 of my PDF, and I can evaluate that again, recall with the CDF function. So if I want to do that in Python, just remember you have to define your mean and your standard deviation, and then you can call the normal CDF with that mean and standard deviation evaluated at 2.42. The probability of that sample mean being 2.42 or smaller is 1.97 times 10 to the minus 146. Okay, that's like 0. That's a tiny p-value. So since it's practically 0, much smaller than the significance level, we would conclude very strong evidence for the alternate hypothesis. Okay, so there's very strong evidence that the true mean is less than 15. Okay, so this is in strong contradiction to the null hypothesis, so we reject the null hypothesis. The freshman 15 legend is fiction. Okay, so let's do another example.
What about bootstrapping your data set to get a more approximation of the standard deviation?
Yeah, well, the standard deviation, the population standard deviation, I believe would still be unknown, and that how this is usually dealt with in practice is, we'll get into this a little bit later in the lecture. What we're doing here is called a z-test. In practice, you use a t-test because a t-test accounts for the uncertainty in that standard deviation approximation. But in general, there's no way to know the sigma for sure. I mean, unless you have, I would say there's no way in most real world scenarios. Okay. Let's see. Any other questions that people want to throw into the chat or? Okay. Okay, let's take a look at the following example. So let's say we have a random sample of 51 Panasonic batteries, and we have a sample mean zinc mass of 2.06 grams and a sample standard deviation of 0.141. So we want to know, does this data provide compelling evidence for concluding that the population mean zinc mass exceeds 2 grams as reported by the company? Okay, so here we're going to take a null hypothesis that mu is less than or equal to 2, and we're going to set our alternate hypothesis to be mu greater than 2. And why do we do that? We pay careful attention to the wording of the problem. Is there evidence that the mean exceeds 2? Remember, the alternate hypothesis is always what you are trying to produce evidence for. So HA should be mu greater than 2, and then the null is the complement of that event. Okay, so let's again set a significance level of 1%. Then what do we know? according to the central limit theorem, if the null hypothesis is true, and in here, let me make a little clarifying comment. So the null hypothesis here is mu less than or equal to 2. So it's not specifically mu equals 2. But when we apply the CLT, we just that boundary value. We just assume, you know, the null is mu 2 or smaller. So worst case scenario are just 2, and we apply this with that boundary value of 2. Okay, so the sample mean has an approximate distribution with a mean of 2. And again, a standard deviation, sigma over the square root of n, appearing in the CLT. We don't know the true population standard deviation, but we will approximate it with our sample standard deviation for now. Okay, so one thing that you can do to run the hypothesis test is to standardize everything. So instead of just working with a normal distribution with this variance, you can subtract the mean, divide by the standard deviation, and convert everything to a standard distribution. And that's called, well, this sort of hints at the name of why we call it a z-test, which is what we kind of have been doing already. So we conduct a z-test, just like we did in the previous example, except now we're going to take our test, which was, we're going to take our sample standard deviation, our sample mean, which was 2.06. We're going to subtract the mean and divide by the standard deviation to get our test statistics. So this is sort of like what you observe in your data minus what you expect according to the null hypothesis divided by the standard deviation. And this comes out to be 3.04. So what this indicates is that what we observe is over 3 standard deviations above what is expected according to the null hypothesis. And again, that's kind of a lot. So over 3 standard deviations. So we would kind of expect that this is an unusual outcome if the null hypothesis were true. Okay, so let's see. Okay, so this Z statistic, since we've standardized it, the nice thing is it's distributed according to a standard normal distribution. So if we want to compute these probabilities, we can just call the normal CDF, you know, with a mean of 0 and a standard deviation of 1. Okay, so let's see how we would do that. So assuming the null hypothesis to be true, how do we get our p-value? Well, our p-value is the probability that the sample mean is greater than or equal to 2.06, which corresponds to the probability that z is greater than or equal to 3.04. So these two probabilities are exactly the same. But once we've standardized, we can compute this probability simply by integrating the PDF of a standard normal random variable. So 1 minus f of 3.04, and we get 0.0012. This is a pretty small value. So because this p-value is so small, smaller than alpha, again, we reject the null hypothesis. We conclude evidence for the alternate hypothesis. So there's pretty strong evidence that the mean really is greater than 2. Okay, which is kind of interesting because what you observed in that data set, 2.06, doesn't seem that much bigger than 2. So you might think, why is there such strong evidence that it's bigger than 2 when it was only 2.06 in your sample? But that has to do with deviation in the sample size. This is still significant evidence that you have over 50 observations with this standard deviation. Okay, and so then you can just see here how there's kind of 2 different ways to evaluate this using the, sort of using the normal CDF where you specify your tailor-made mean and standard deviation, or using the normal CDF where you've standardized it and you're just doing a mean of 0 and a standard deviation of 1. So either of these work fine. You get the same answer, which is 0.00, about 0.0012. Okay, so let me sort of recap here, summary of hypothesis testing and the z-test. So first, you want to identify the parameter of interest and describe it in the context of the problem. So you determine the null and the alternate hypothesis, right? The alternate hypothesis is always the one that you would like to obtain evidence for. You choose a significance level alpha, say 1% or 5%, and then you compute your test statistic under the assumption that the null hypothesis is true. Okay, so you can use the CLT for this. You compute your test statistic Z as the sample mean minus mu over sigma over the square root of n. Okay, this can be done whether your variable is quantitative or whether this is referring to kind of the mean that you would expect from counts in a coin toss. But like we saw in our coin toss example, like if you really were dealing with coin tosses, so if the data that you're observing really is binary, yes or no, and your alternate hypothesis involves a proportion, you can apply the CLT to a sum of Bernoulli's, and in this case, the test statistic comes out to be the sample proportion minus the true proportion specified in the alternate hypothesis or the null hypothesis divided by that standard deviation. I just thought I'd write it out there so you can kind of see. Yeah, I mean, you can compute it from scratch too, but that's basically what you get when you apply it to the Bernoulli's. Okay, so using the sample data, you compute your p-value, and then you compare your significance level to the p-value to decide whether or not the null hypothesis should be rejected. Okay, so the p-value is really important. A lot of times you want to report the p, not just whether you rejected the null hypothesis or not, because it really quantifies the strength of the evidence. So, a p-value of 0.049 is quite different than a p-value of 0.0005. Okay, and here's your little cheat sheet for 1- and 2-sided hypothesis testing. So, like we sort of saw in some of our examples, depending on the alternate hypothesis, you might be calculating the area in just one tail, or you might be calculating the area in both tails. So if your alternate hypothesis contains a greater than inequality, your test statistic is usually here on the right side, and your p-value is this area in the upper tail. On the other hand, if you have a less than in your alternate, you're calculating the area in the left tail of the distribution. And if you have a 2-sided test, you have a not equals in your alternate, then you're calculating the area on both sides of the tails. Okay. Okay, and then I sort of hinted at this earlier, but to make this a little more precise, I said, well, what details are we kind of sweeping under the rug? Well, for a z-test, you're supposed to know the population standard deviation, but you don't. So you're using the sample standard deviation. So in practice, we actually would usually use a t-test. And this is a good thing to do if the sample size is small. If the size is large, it really doesn't matter. For a large n, S and sigma are so close to each other that it really doesn't matter. But if the sample size is small, it's more important to take this into account. And in this case, it's the test statistic is distributed according to a t-distribution, which we won't go into many details about what that looks like or anything, but just so you're aware of it. The t-distribution is very similar to a normal distribution, except it has, as we saw earlier in the lecture, a little bit heavier tails. Okay, and so here you can see just a little plot, an interactive plot, illustrating how the t-distribution compares to the normal distribution. So the normal distribution is black, the t-distribution is red, and you see even for a sample size of 11, they're pretty close, but the t-distribution has a little bit heavier tails. And if I increase this even more, you can see that the agreement gets even stronger. What would be considered a large sample size as a percentage of the population? Okay, great question. So it's not really, the size of the population doesn't really come into play. Usually we just think about what's a large sample size. And again, there's not like a perfect answer to this question, but if I were going to throw out a number, I might say 30, ish. So if the sample size is maybe over 30, you're probably fine to do a z-test. But smaller than that, you probably want to do a t-test. And you can always just do a t-test just to be safe.
Well, I was actually thinking if you had a sample of say 30 for 100,000 people, I don't think it would be as representative of say a sample of 30 for 100 people. So, you have like 30% if 30 for 100 people, population of 100 versus 30 people for a population of 100,000 would be, like 1/3%. That's what I was wondering. So you don't actually look at it as a percent of the population?
No, generally not. Yeah, generally you don't. I mean, if you're thinking about, say, a quantitative variable or you're taking, if you have a sample of 30 from a population of 100, or if you have a sample of 30 from a population of 10, you have about the amount of, I guess, power for making an inference about the population mean. So.
Okay, thank you.
Okay, and yeah, you're welcome. And then isn't 40 commonly accepted in basic stats as a condition for assumed normal? Yeah, I would say 40 is also a reasonable number. Sure. 30, 40. Like I think it may vary a little bit with what textbook you're looking at. Yeah. If you want to go with 40, that's cool. Okay. So so we see that, yeah, it has heavier tails, but as n gets large, it becomes the same thing. And I guess in the notes we put, for a sample size greater than about 20, the normality assumption is generally accepted as reasonable. But yeah, maybe you want to say 30, 40. Okay, 50 is definitely fine. Okay, so let's talk a little bit about errors in this testing. So there's basically two different types of errors that can occur. Here's a little table that's kind of helpful to keep in mind, right? The null hypothesis might be true or it might be false. The alternate hypothesis might be, we might reject it, and we might fail to reject it. So here are the kind of the outcomes of the hypothesis test. And this is kind of the underlying truth of what's going on. And so there's two different errors that can happen. In a type 1 error, the null hypothesis is true, but we reject it. In a type 2 error, the null hypothesis is false, but we fail to reject it. Okay, so it's kind of like Type 1 error, we were perhaps a little too gung-ho about drawing conclusions. And in a type 2 error, we weren't proactive enough in drawing conclusions. Of course, it can happen, but those are the two different kinds of errors. So it's helpful to, so the probability of making a type 1 error, this can be quantified exactly. This is the significance level alpha. So if you take a really small alpha, then this is very unlikely to happen. But there's a downside, right? If you take your alpha to be small, then you're going to make a lot more type 2 errors. Although the exact for type 2 error is hard to quantify precisely, but there's definitely a relationship. Okay, so for example, let's say we're doing drug testing. We take a null hypothesis that the drug has no effect on the disease. So in a type 1 error, we detect an effect that's not really there. And in a type 2 error, there is an effect, but we don't detect it. Another kind of good example to think about is thinking about somebody that's on trial where the null hypothesis is this man is innocent. Then a type 1 error convicts an innocent person, and a type 2 error lets a guilty person off. Okay, and in certain situations, a type 1 error may be considered a lot more serious than a type 2 error, but of course you would prefer not to make either of them. Okay, so another thing to kind of mention is that in this era of big data, where we have these massive data sets with an enormous amount of variables, you're bound to discover patterns just by chance. And those patterns might not really be there. So this is called p-hacking. So, the p-value measures how extreme the observation is compared to the significance level. But said that several times. Let me just discuss here the misuse of hypothesis testing. So the basic idea is that if you do enough hypothesis tests, eventually, you'll have a type 1 error, right? If you set your alpha at 5%, okay, if you do 100 hypothesis tests, you'll make a type 1 error about 5 times. And so if you just do enough of these, then you're going to make a number of these errors, and this is referred to as data dredging. So one thing that you can do to try to compensate for this is cross-validation. Maybe you split your data in half. Maybe you sort of check for patterns on a subset of it, and then try to validate it on another part of the data. And we'll discuss this a little bit more later in the class. Okay, so let me see how far we got. Almost to part 2, so that's pretty good. Actually, why don't I don't think I'm gonna probably get through the confidence intervals in 1 minute. So why don't we stop there for today? This was a lot to cover, but this was sort of my plan. I was thinking that Thursday we'll also cover the 2 sample hypothesis tests, and we'll talk about how to actually do those in Python, how to actually run the hypothesis tests explicitly in Python. And then we'll also be talking about time series analysis a bit on Thursday. Okay, well, let's stop there for today. Are there any other questions?